Hello viewers and welcome to another episode of Space Science with Python. Now last time we finished our machine learning asteroid spectra project that is here in this folder called ML1 asteroid spectra, and we created now 14 Jupyter notebooks that we use to fetch the data, parse the data, enrich the data. We created a machine learning model on support vector machines and deep learning and also some autoencoder. So before we start with the next machine learning project or with the next larger science projects on near-Earth objects, I would like to continue a little bit with the, let's call it, general tutorial session that is here numbered through from number 3, set up VS Code, to now 23, Philae landing, and now the next one, 24, is now here in almost in a pull request. You may remember in our last sessions, in the general sessions, it's like a few months ago, we created a small Comet database. We took a look at the CNP comets, the Oort cloud. We checked the Tisserand parameter and the rendezvous with Jupiter. So for example, here we checked here, for example, created a small figure. Now this is a little bit too large, where we plotted the Tisserand parameter of the P and C-type comets and saw that the P-type comets are astrodynamically linked with Jupiter and the C-types are not. And now, let me go back. And then we also, we're talking about observational bias effects that we mostly observe only the larger ones and smaller ones only if they are approaching at us more closely. And then we took a look at the comet in 3D. So we took a look at the shape model of the comet Churyumov-Gerasimenko that was visited by the Rosetta Philae spacecraft back in 2014-15. Afterwards, we also took a look at the Philae landing. So we used the kernel of the Philae lander and saw how the spacecraft was bouncing on the surface until it found its final landing spot in a cavity. So it was not really found, it was more like I would say an indirect passive process where the Philae was bouncing around uncontrollably and then got stuck in some kind of cavity. And today I would like, or today in the next time, I would like to continue a little bit with the Comet session to extend a little bit our knowledge on Comet data. So today we will take again a look at the comet Churyumov-Gerasimenko. Here is a small picture from Wikipedia taken by the Rosetta spacecraft, and you see this two globe model or shape of the comet with a larger one and a smaller one connected by some kind of, let's say, bridge between these two bodies. And what we are going to do today is we will take a look at the orbital elements of Churyumov-Gerasimenko. And for this, we will also download a SPICE kernel again, an SPK kernel. So maybe you recall that the SPK kernels in SPICE are the ones that contain astrodynamical or trajectory information of objects like spacecraft and also asteroids, planets, and so on. And here from the NIF website or repository, I downloaded the SPICE kernel for Churyumov-Gerasimenko. Surprisingly, it's stored in the folder former versions, so I don't know why, because I did not find any more recent one in the current folder. So we will use this one here, a SPK kernel that is valid between the years 2004 to 2016. So let's have a look and let's see what we are going to do. So today and next time, the tutorials or videos are a little bit linked to each other. You see here, I call it the 67P changes number 1, and the next time it's number 2, because we will take the data from the Minor Planet Data Center on our database that we created in video, in video 16, and then we will compare the results from the database with the results from the SPICE kernel, and then in the video next time we will try to explain how these changes happen. So let's dive into the code. You see here we are not using Google Colab as the last time or in the machine learning project. We are using VS Code again with the Docker remote container session. And if you do not recall how to create this remote container session, either take a look in at the setup from months ago. The link is in the description, or just wait until the end of the video. I think I will create a small recap on how to create a remote container, so you can simply use this navigation menu in YouTube and click on the corresponding section, and it's at the very end of today's tutorial. So let's go now through cell by cell. We are not now making a live coding. We are going a little bit with a higher velocity through the code. The code is on GitHub, of course. You can take a look at it so that we have more time explaining the code. Now, cell number 1, quite simple. We are just importing modules like the SQLite3 and SpicyPy and Pandas and Matplotlib for plotting later. So this does not need any explanation. I already executed it, so it's now written the number 9. So I shouldn't maybe execute it from now on. In cell number 2, we are connecting to our Minor Planet database. So it's not really the actual Minor Planet data center, but really the database that contains the parsed, the downloaded, parsed, and stored data in our SQLite database. So, and here, this is what we do in line number 2, where we connect to the database, and then in this line 5 to 9, we are creating an SQL query where we say that we would like to select the name, the perihelion, semi-major axis, aphelion, eccentricity, the argument of perihelion, and the longitude of ascending node from the only table called Comet's main, where the name is like 67P. So yeah, hopefully we will only extract one object, and in this case, it's hopefully Churyumov Gerasimenko. Now, a small recap what these values mean. So the apparently the name is the name. The perihelion is the closest distance between an object and the sun. So what is the closest distance between, in our case, Churyumov Gerasimenko and the sun? The semi-major axis is, so to speak, something like the radius of an ellipse. So the larger radius. So we have like the smaller, the smaller, let's say, the minor axis and the major axis. Then we have the aphelion, which is like the most farthest away distance from the sun. It only applies for objects that have a closed orbit around the sun. So a closed orbit is given by the eccentricity. So the eccentricity is a value that provides the information about the shape of the orbit. 0 means the perfect circle. A value between 0 and 1 corresponds to an ellipse. As a value that corresponds to a perfect 1 is periapsis, and the values larger 1 is a hyperbolic shape. So the argument of perihelion and the longitude of ascending node, these are values that are linked to our reference frame. And our reference frame here, or our reference plane, is the ecliptic plane. That is an imaginary plane that is drawn by our home planet, so by Earth. So imagine a table, and on this table, the Earth is moving perfectly on this table. So this table is defined by the movement of the Earth, and all other planets, they are not lying on this plane. Their individual plane is a little bit tilted by these their plane is a little bit tilted with respect to our ecliptic plane, and it's given as an inclination. Now I see I did not extract the inclination, but yeah, that's fine. But the argument of perihelion and the longitude of ascending node, they provide information how this ellipse is tilted and shifted with respect to this plane and to the reference coordinate system called ecliptic J2000. Now, more details about the reference frames and so on, they were provided in the past, so I will not go into detail here now, but these are now, let's say, the most important orbital elements, although I just checked that I forgot the inclination. Anyway, executing this code segment number 2 leads us now to number 3, where we simply plot the results. And we see here the name of the object, Churyumov Gerasimenko, so perfect. We have here the perihelion in AU, so 1.2 AU. We have the semi-major axis of 3.45 and an aphelion of 5.7. Now, the inclination is, I think, quite small. I mean, we can simply go back here, check maybe the Wikipedia page, but now I see cannot go back. But I think the inclination was below 10 degrees, so let's say quite close to the ecliptic plane. And yeah, when you see also here the aphelion of 5.7, this corresponds, of course, to a distance that is at around the orbit of Jupiter. So yeah, this object approaches Jupiter quite closely, and in fact, Churyumov-Gerasimenko is an object or a comet whose orbit was altered by Jupiter. So we will see in the next video how the orbital elements are changing. Next session, we go now here in cell number 4, where we simply call our spice kernel meta file and we extract the gravitational parameter times the mass of the sun that is needed for our spice functions in a moment. And here in cell number 5, we define a datetime range between 2004 and 2014. And in this range, we will see how the orbital elements of the comet change based on the spice kernel we just downloaded. So of course, the value here from the database is static, so it doesn't change at all. Our spice kernel, well, let's see if the values change in this 10-year date frame. Now here, let's go to cell number 6, and here we are creating a data frame for Churyumov-Gerasimenko. We create a column called UTC in line 5, where we put the datetime range in there, and then we correspond a second column with the corresponding ephemeris time using the spice function UTC to ET, and then afterwards we can simply compute the state vector of Churyumov-Gerasimenko for each ephemeris time, so for each time step between 2004 and 2014 with a divided in 1000 steps, where we compute the orbital elements of Churyumov-Gerasimenko. So this is the target ID with respect to the sun. The ID is 10 in the ecliptic J2000 reference frame, and here the lambda x or lambda x is in our case the ephemeris time. And based on the state vector, we can then afterwards compute the corresponding orbital elements of this comet and put the resulting array into another column. So this is now cell number 6, and then we can move to cell number 7, which is really simple. We are simply extracting all individual orbital elements from this array and assign it to individual columns like the perihelion, the eccentricity. Here's also the inclination, by the way, longitude of ascending node, and so on. So this is quite simple and straightforward, so that we can finally move to cell number 8, where we are then plotting, in our case, the perihelion eccentricity and argument of perihelion. So yeah, you can also take the inclination and so on, so feel free to extend it a little bit, where we are creating 3 plots plotting the perihelion, eccentricity, and argument of perihelion versus the time. So from 2004 to 2014, we draw a horizontal line here. It's just a horizontal line because it's a static value from our database, so it doesn't change at all. And here, before, we are plotting the orbital elements based on the spice kernel, or the information that is stored in the spice kernel. And you see here the spice values are then solid orange lines, and the horizontal line from the Minor Planet Center data is an orange dashed line. Yeah, doing some more formatting, like providing or plotting a grid, a legend, and so on. And then afterwards, we can also store the information in 3 individual plots. In this case, I will not upload them in the repository, but by executing this script, you can simply create these figures. So let's take a look at the figures. And this is like the first one, where you see the perihelion in AU of Churyumov-Gerasimenko versus the time from 2004 to 2014. And as I already said, the dashed line is the constant MPC data, and the solid line is the data from the SPICE kernel. And you see here some changes, but before we dive into the data, let's take a look at the graphs. We have here the perihelion, we have here the eccentricity, and we have here the argument of perihelion in degrees. So let's take, for example, the eccentricity. You see here the dashed line, the solid constant line at around 0.65, and you see it doesn't change at all. Again, it's a constant value. But for our SPICE kernel, this does not really apply. The value changes over time. So in the beginning, 2014, the orbit of Churyumov-Gerasimenko was less elliptical, let's say, so more circular, although a value of 0.6 is very elliptical, but I think you get what I want to say. And it was at around 0.6325. Yeah, so this is like the value it was there. And then the value increased over time. So in the time range of, let's say, 4 years, it increased to around 0.64. So yeah, it's quite significant, you see here. Then afterwards it went a little bit down again, and then it's more like a plateau, so almost constant, but not as constant as a constant value from the minor planet center. You see here also that the corresponding perihelion at the time changed from 1.29 AU to 1.24 AU. So the distance between the comet and the sun, or the closest distance, decreased and decreased and decreased over time. Yeah, I don't know how it will behave in the future, but this is the behavior of Churyumov-Gerasimenko between 2004 and 2014. And of course, the changes are, one can say, are they really significant? Well, consider what in 1 AU means. It's the average distance between the Earth and the Sun. So we have here a difference of 0.03 AU, so that's a few million kilometers. And of course, it depends a little bit on your use case, what kind of data you would like to use, right? I mean, do you want to compute for all the timestamps, the orbital elements and state vectors, or are you fine with some very rough estimations or fixed values from the minor planet center? It's up to you what you'd like to use. If you are considering to compute a high precision maneuver to an object, you should maybe go for the SPICE kernels, but for, let's say, some more general science task where you are, for example, describing the statistics of all the comets out there, use the minor planet center in this case. But the most important question, though, is why does it change and how does it change? And to answer this, we will take a look next time at the interaction between Churyumov-Gerasimenko and Jupiter. So see how the orbital elements behave and change over time, especially during close encounters with this object. And we will not make a numerical approach, but really an analytical approach. So it's not as precise as an n-body simulation where you consider all gravitational perturbations of all objects. You just take Jupiter and the sphere of influence, but it's something for starters and something to give you, to get some kind of feeling. So I would say welcome back to this small general tutorial again before we start with a new project and go through the code. Let's re-dive into SPICE a little bit. We will need it also in our future video. And until then, I wish you happy coding and see you next week. Okay, and as promised, a small recap on how to create a remote container session for this tutorial series. So most importantly, what you need is Docker installed and running, and you need VS Code. So just download the corresponding software and you're fine. Now you are opening the Astronis YouTube tutorial session, and you take the data from GitHub. You get also the corresponding Docker file and some other meta information that is stored in this .dev container folder with the corresponding JSON. So this provides some more additional information. Now, on the Mac, you press the Shift, Command, and P button so that you see the command bar here on the top of VS Code. I think for Windows, it should be something similar, like, I don't know, Shift, Alt, P or something. So try it out. And there you see already here on the top the commands, but let's just write down remote minus containers, and there you see different options. The very first time you create a folder, you should click on open folder in container. It will also ask you what kind of folder is your remote container session. In this case, it's the Astronaut's YouTube tutorials. In my case, I would like to maybe rebuild it. So I simply click on rebuild and reopen in container. In this case, it will not ask me where the data is. So let's click on this one. And I think this would take some time. So yeah, so you see now everything is building, but I think some stuff is already in the cache, so it should be quite fast. Yeah, it's going really fast. So I think now the extensions are installing. Yep, the extensions are defined in the JSON, and now it's almost done. The next download, next extension is being downloaded, and everything is now fine. The Python extension is okay. This is I have never seen. It's from Pylance, I think. Yeah, I don't need it now. It's fine. You can now install Pythons now, or yeah, I can remind later. It should work anyway. But what's more important is that if you are running now a script, so for example, just running this one here, either it is automatically connecting to your kernel, or it will ask you to connect to a kernel. And there are different options, I think 3 or 4 options. And check the Docker file, what kind of Python version we are using. It's 3.9. So there should be a version called 3.9, and the default is then something like Python 3. You have to choose this one when you want to run the Jupyter Notebook, because in this kernel is Python, but also the corresponding libraries that are being installed based on the requirements.txt. If you choose, for example, Python 3.7, I think this is the default of this image, then you will run into an error, because it will say, I cannot find any library. So this is all you need for now for some happy coding. You can also create now a new terminal here, and if you just simply write IPython, you see I have now here Python installed, and now I can run simply import numpy snp, and everything is there. So let's check if it works. Random rand int 5. Oh, 1 4. Yeah, perfect. It runs. So that's how you create your remote container session. If you need more details, the link is in the description, where I was talking about it, where I talk about it in more detail.